Alright, this lecture is the continuation of our discussion of ionic compounds from last class, where we talked about simple binary ionic compounds, which would be those that did not have polyatomic ions or transition metals. They were all representative and only had two elements. So we're going to continue with the two element theme and still look at binary compounds, but we want to introduce transition metals. And transition metals have a slightly different way of naming them. Just based on their position and the way their electrons are arranged, they have the possibility to have multiple charges. So let's take a look at how that works. With the compound FeO, I have a metal and a nonmetal, so I'm still meeting the ionic criteria. If we notice, since it's only FeO, we're still binary, so we're going to apply the same rules. The difference is going to be that because it's a transition element, I'm going to need that Roman numeral to denote the charge of iron in this particular compound. So I know it's iron, and I need to know the charge. So I'm going to use some deductive reasoning to do this. The awesome thing about this is that the anion part, the nonmetal, in this case oxygen part, is never going to be variable in charge. They'll always be the same. And I know that all compounds have to be neutral. We talked about that last time, so that the same number of electrons have to be lost by one thing as gained by another. And since oxygen is in group 6 or 6A or 16, depending on how you want to think of it, I know it has to have a -2 charge. And if it is -2, then iron has to be +2. I have to have a neutral compound, so that's the only charge of iron that will make this neutral. And so we're going to designate iron with a Roman numeral of 2. And so the name of this compound, then, if I name the iron, before we would name something like sodium, we would just say sodium. In this case, we have to say iron 2, and then we name the back part of the compound, which is from oxygen becoming oxide, just like we did last time. So the only new piece of information is adding that charge right here, adding this charge into the compound. So it's really not that difficult. So let's look at another example, Cu2S. I'm going to name the first ion, and I'm going to notice it's a transition metal because it's located in that D block. It's not a group 1, 2, or 3 metal. So I'm going to know I'm going to use a Roman numeral, but I need to know what that Roman numeral is, and it's going to be the charge of the ion. So again, how did we find the charge with iron before? Well, we used that good old deductive reasoning. So let's start down that road again. We know all compounds have to be neutral, and we know that sulfur is in group 16 or 6A, so it has a -2 charge. That means that the total charge for the coppers has to be +2. But what's different this time is that I have 2 coppers. Since I have a +2 that has to offset the sulfur, and I have 2 coppers, that means each copper must be +1. And so the Roman numeral for my coppers would be copper 1 sulfide. So again, naming it just like a binary ionic compound with the addition of the charge in parentheses. One other example, MnO2. I know this is binary and I know it's ionic because it's got 2 elements and it's a metal and a nonmetal. So I'm going to name the first ion, realizing that I'm going to need a number in parentheses because it's a transition metal. So Mn is manganese, and I'm going to need to know what that wonderful charge is. So we're going to use the same deductive reasoning we've used before. All compounds are neutral, and I know that oxygens are -2. That means that if I have 2 oxygens, each with a -2 charge, that I have -4 on the oxygen side. That means that the manganese must be +4. That's the only way it will offset the oxygen charge, and so my name is manganese 4 oxide. So why do we have to do this in the first place? Well, if you remember, the metals in group 1A, 2A, and 3A, or 13 if you will, have single charges. They were definitive. We said they're always +1, always +2, always +3. Transition metals just don't behave that way because of the way their electrons are arranged, and this is something we'll pick up in a later chapter. They have the ability to adopt several charge states. Generally, most of them will do at least 2. Some of them will do much more than that. For example, here we have two different copper oxide compounds. We can have Cu2O and CuO. Both of these are legitimate compounds. We can't just say copper oxide because there's more than one copper oxide. Which one are we talking about? This could be the difference in, being in your kitchen and adding sugar or salt. I mean, they kind of look the same, right? But we need a definitive name for what they are. And so when we have copper 1 oxide, the charge on copper is +1. That occurs when I have two coppers needed for an oxygen. Oxygen becomes oxide at -2. So if two coppers are required, that's copper 1. If I have one copper and one oxygen, that means that both of the electrons are coming from a single copper, and it's +2. That's a totally different compound, and it has totally different reactivities than the other one. And so we need to be able to make these distinctions. Alright, there are some transition metals that do not require these Roman numerals because they are always a certain charge. Due to their locations, they're not really able to do multiple charge states, and when we come across these, we need to recognize them. The first one is zinc. Zinc is always +2 and never anything else. Next is cadmium, also always +2 and never anything else. Last but not least is silver, which is always +1. Now, silver really does have some other oxidation states, some other charge states that it can have, but for 99% of daily life, you're never going to see those. So we're going to add silver to the list and say that it's always +1. So you just need to memorize these. Pretend like zinc and cadmium are part of group 2A and that silver is part of group 1A, and you'll be good to go. So an example of naming these would be much like naming a normal non-transition metal compound. So if I have Ag2O, the first thing I want to do is name the first ion. The first ion is silver. Even though silver is a transition metal, because it's always +1, we're not going to write it. We're going to treat it just like we would sodium. And so name the second ion. Well, O is oxygen, but when I change its ending to "ide," it becomes oxide, and away we go, just like the compounds we did the other day. Zinc also behaves this way, so we'll name the first ion. It's just zinc. It's always +2, even though it's transition. And then Cl, we will name just like we did on day 1, and we'll say chlorine becomes chloride, and there we go. Our compound is zinc chloride. We don't need Roman numerals for these. It would be redundant. To say zinc 2-chloride would be like saying I go speedy fast. That's just a double use of the same modifier, and so we don't need that in our compounds. If we want to write some transition metal compounds, it's similar to writing ionic compounds. In fact, we don't even have to consult a periodic table for our metals because the Roman numerals in the parentheses is the charge, and so we've limited the amount of time we have to spend looking at a periodic table. So we're still going to follow the same rules. We're going to write the symbol in charge of each ion, just again recognizing that the Roman numerals give me half this information already. So when we write them, the iron 3 translates to iron +3. Bromide is Br, and I find that it's in group 7 on the periodic table, which means it has a -1 charge. We'll apply the same logic we did last time. I have 3 positives on the iron, and I need 3 negatives from the bromines. That means I need more bromine. The least common multiple of 3 and 1 is 3. And so I've got 3 charges on the iron. I need 3 charges on the bromides. So I pick up 2 more, and my formula becomes FeBr3. Again, if you prefer to just follow the charge swapping method, you can do this. The 3 from the iron goes over to the bromine. The 1 from the bromine goes over to the iron and becomes understood. Anytime I bump into ionic compounds that aren't binary, this means they contain at least one polyatomic ion. Now, these can have transition metals. They cannot have transition metals. That doesn't matter. This is a whole nother category. These are ones that have more than 2 elements present. And so when they do that, we have those polyatomic ions. Well, let's just break down that word so that we can take a look at what a polyatomic ion is. Anytime you see ion, that means it's something with charge, so it can't be neutral. And number 2, anytime something is poly, that means many. And so polyatomic means that it has many atoms, more than one. And so it's that simple. There are several that I gave you to memorize, but here are a few just to refresh your memory. CO3 negative 2 is called carbonate. Notice that is a collection of atoms, 1 carbon, 3 oxygens, that carries a negative 2 charge. So anytime I see a group of atoms like that carries a charge, it's polyatomic ion. Here is a few more of the ones that you've got to memorize, but this is by all means not all the ones you're responsible for. SO4 negative 2 is sulfate. SO3 negative 2 is sulfite. ClO4 is perchlorate. ClO3 negative is chlorate. ClO2 negative is chlorite. ClO minus is hypochlorite. PO4 3 negative is phosphate. C2H3O2 negative is acetate. OH minus is hydroxide. NO3 minus is nitrate. NO2 minus is nitrite, and NH4 plus is ammonium. Notice that ammonium is the only positive polyatomic ion mentioned. Again, I'm not going to leave those on the screen very long because you have all 20 of those plus some more to make 20 in a sheet that you're supposed to be memorizing. So how do I recognize compounds that aren't binary? That's pretty simple. I'm going to have a polyatomic ion present, and there's going to be more than 2 elements. So if I count on my fingers the number of elements, there will be more than 2. There's only one positive polyatomic ion, and so there are only 3 possible types of non-binary ionic compounds. There are those where ammonium is the positive ion, and I have some negative nonmetal. There is the possibility to have some metal and some negative polyatomic ion, like NaC2H3O2, for example. And then there is a possibility to have ammonium acting as the positive side and some other polyatomic ion acting as the negative side. For example, NH4OH, ammonium hydroxide, would fit this bill where both members were polyatomic ions. That's why it's important that you memorize those so that you recognize them when you see them and you know that it's not a molecular compound just because it's not containing a metal. Alright, so how do I name non-binary ionic compounds? Well, it's really not that difficult. We're still going to treat them just like we did normal ones. It's just that the ions have their own names. So instead of going to the periodic table to get the names, we just take the name of the ion and slap it on the back. It's pretty simple. So my example, Na2CO3, naming the first ion, tells me that this is sodium. Sodium is a representative metal, so its name is sodium. If I take a look at CO3, I know this should be a polyatomic because this is an ionic compound. It contains a metal, and it's got more than 2 elements, so that means there is a polyatomic somewhere. CO3 negative 2, hopefully you'll memorize it before long, but for right now you can tell from your sheet that that is carbonate, and so naming the second ion is that easy. You just write down carbonate, and so Na2CO3 is sodium carbonate. We don't change the suffix, we just write it down because that's its name. A few more examples. FeOH3, this combines both of our new ideas. Fe is a transition metal, so when I name it, I'm going to need its charge. That's iron. I'm going to use my good old deductive reasoning to figure out what that Roman numeral should be. If I look on my sheet, I'm going to see OH minus has a charge of -1. I have a compound that has to be neutral, and I have 3 things that are -1. If that's the case, that means that I have to have a -3 for the hydroxides, which means I have to have +3 for the iron. So using what we learned just a minute ago, in my parentheses I'm going to put the 3 for the iron, and I'm going to just name the back half of the compound knowing that OH minus is hydroxide. Boom, there you go. NH4Cl, notice no metals, but I know it's ionic because I know NH4 positive is an ion. So we name the first, it's ammonium. We name the second, that's chlorine, but when it's in an ionic compound, we change it to "ide" and it is chloride. Look at that. Excellent. Just like binary ionics for the backside, but we're using a polyatomic in place of the metal. NH3PO4, again, is a similar compound, only it contains 2 polyatomics. Name the first ion. NH4 is ammonium. PO4 is phosphate, and we're done. One more example. Cu2SO4, first ion is copper. Second ion is sulfate. And I've got to realize that we're going to run out of time on this one, and so I'll go over this one in class with you when I can.